Hey physics, this is Mr. Hausman. We're going to take a look at parallel circuits today. That's one of our last topics in the study of physics. Parallel circuits have a lot of applications in everyday life. In fact, you can find parallel circuits in your house. Most of your house and the neighborhood is wired in what we would say as parallel. How is that circuit built? It's built in parallel. What we mean by that is a couple of things. One of the huge benefits of parallel is if one light or one piece of electronics, right, if one light goes out, the others stay on. Can you imagine what it would be like if you went out for the day and some light bulb in your house just burned out because it was older in age? And what happened is that all of the lights in your house went out at the same moment as the one that was bad. So you'd walk into a house and you'd have to go around and try to guess and try to figure out which one. And that would be terrible. There's another upside to parallel circuits is that if there are two light bulbs in parallel, they both get the same brightness. So that would be great. We would not want to have a situation where the more lamps we have in our house, the dimmer they get. That would be very undesirable. So the best feature, the one to remember, right, is if one light goes out, the others stay on. Well, why does that happen? Let's take a look and pretend we are looking at the electrons. But we're not going to talk about the electrons. We're going to personify them. We're going to pretend they're little stick figures. And what they're doing is they're carrying energy from the battery. Remember, the battery, whose symbol is long line, short line, positive, negative terminal, right? This is the source of the push or the energy for the circuit. That's why a dead battery won't turn on a flashlight. That's why a cell phone that's run out of charge. Now be careful. Remember, cell phones that we charge them, but what we're really doing is putting energy back in them. Okay, so let's back to the electron dudes. See the little electron dudes? Here's how you can tell a parallel circuit. And here's why if one is damaged or burns out, the other one works. Each of these electron dudes is going on a trip, and that trip is only in one direction. So they're getting pushed by the battery, and they have a choice right here at something called a node. Do you see that these electrons can go one of two ways? So pretend it's a split in the road, and they can either go straight or they can bend 90 degrees. There's nothing that says they are told to go one way. When you get to a node, it's like a fork in the road or a path, and you can go either of those two routes. Now, if you take the first path, you go through the first resistor, and then the electron dudes would give up their energy at the resistor, and then they'd go back. If, on the other hand, you took the upper pathway and you went around the outside corner, went through the second resistor, and then came back, notice that what you would never do is you would never go through both resistors. So it's either you go through resistor 1 or you go through resistor 2. So what happens if resistor 1 is damaged? What if it's a light bulb that's burned out? Well, I guess all the electrons will just keep going on the other pathway. A broken light bulb means that it's just no longer part of the circuit. So if this one was broken, what would happen? Well, everyone would just go to the outside path. Now you might say, but it would be brighter because now there's more electrons. Brightness is a function of how much energy is each electron carrying. And as it turns out, they don't carry more energy, but they simply just go straight. So that's an advantage of parallel circuits. Okay, now here's another key idea about parallel circuits that's different than series circuits. Let's clean this up a little bit. Okay, let's go to a new color. Let's go to red. What you notice if you think about batteries is, let's pick a battery voltage. Let's call it a 9 volt. The 9 volt batteries are like the kind that's in a smoke detector. They're little rectangular ones. They have the two buttons on the same end, but they're most commonly in like remote controls and smoke detectors. So batteries provide energy, and we call that voltage. So if you're an electron leaving the positive terminal of the battery, because that's where the high energy is, until you go through a resistor, you keep your energy. See how each of these buckets is still full. Remember, we're personifying each electron as if it's carrying a bucket of energy. Okay, so until you go through a resistor, you keep your energy. So do you notice that I've color coded this? And the reason why I chose red is because it's like a hot color. It's like a high voltage color. Let's make it like almost like a warning color. Then when you go through a resistor, you lose voltage. You've seen me use this symbol. It's kind of like a tent, and it basically means we're going to drop off or we're going to lose some voltage. Okay, each of these resistors needs to get some. Now, one of the rules of circuits, though, is that by the time the electrons are going back to the battery, do you notice that their buckets are empty? In fact, they're not even carrying buckets. But a better way of thinking of it is an empty bucket. So they go from full, which is 9 volts, and it's 9 volts here, and it's 9 volts here. But on the way back, it's 0 volts. So we're going to color code that with a cool color, like a low temperature color. And I don't know if that makes any cognitive sense, but we're going to have the high voltage be red and the low voltage or low energy color be blue. And so we're going to call that 0 volts. In fact, electrons always have 0 volts when they come back to the battery in any kind of circuit. Okay, so ask yourself right here, what's going on when you get to this point? Well, I'm seeing a red color turn to blue. So what does red stand for? Oh, that stands for 9 volts. And blue stands for 0 volts. And so we get a loss of voltage of 9 volts. But the other resistor way out here also goes from red to blue. So that's also losing 9 volts. So apparently every single resistor in a parallel circuit, because it has a pathway back to the battery, right? Every single electron that goes through the middle path or the outside path always is full of energy. It basically says that every resistor will get the same voltage as the battery itself. Okay, now these two principles, the principle that the voltage stays high until it goes through a resistor and it comes back 0, also explains why every light bulb is the same brightness. Okay, so remember we talked about why if one goes out, the other one stays on. And now you understand a little bit about why if they maintain the same brightness, because they're both losing 9 volts of energy. Okay, so another way of saying that is that the total voltage of the battery is equal to the voltage at the first resistor, and it's also equal to the voltage drop at the second resistor. Now, you can't solve this equation, but what it says is that all paths get the full voltage of the battery. That's an important principle, okay? Now, something else you need to know about parallel circuits is that they're actually kind of dangerous. When they were inventing electricity back in the late 1800s in North America, originally towns and cities were wired in series. If you wanted to add a light bulb, it would cause the other light bulbs in your house to get dimmer. So people would only have 1 or 2 light bulbs. Can you imagine that? So people were not very satisfied with that. So a company realized that if we wired the entire neighborhood in parallel, then we could add as many light bulbs as we want, and that would be a good thing, right? We could have brighter cities and homes, and we could work at night in factories, whatever you need. But here's the problem. The more light bulbs you add, 1, 2, maybe a third one out here and a fourth one out here, and we'd have to wire them, right? We'd have to connect them. Connect. Every time you do that, every time you add a resistor, the total resistance gets smaller. Oh, that sounds like a good thing. But here's the problem. When the resistance goes down, the current increases for the circuit. And current is what is incredibly dangerous in a circuit. Remember, I stands for current. The current, the total current that flows when you have more pathways actually goes up, and that becomes a problem. That's what causes our modern homes to have circuit breakers. They're in your basement or they're in your garage. It's an electrical panel with a whole bunch of switches in it. And if you overload a certain room or place in your house that is all in the same circuit, some of these switches will turn off automatically, right? They get flipped. And you need to unplug those electronics, and then you go to the basement circuit breaker and reset it. Probably should do that, or have your parents do that if you overload a circuit the first time. It's not terribly dangerous, but you do need to know not to just start flipping random switches. Okay. So let's talk about why the resistance decreases. This is why. This weird formula right here is how you add the resistors. This is how you get the total resistance in parallel. And that's a weird way of writing it. It basically says that you take whatever value the first resistor is, let's make it be 2 ohms, and you write it as 1 over 2. Right? Because it says take the reciprocal. Is that a math word we've heard of? Maybe you've heard it called an inverse. So what's the inverse of 2? Instead of 2 over 1, it's 1 over 2. Now let's say R2 is 4 ohms. Well, now we have to add those two fractions together. And that is uncomfortable for some people, but we will make sure that most of these problems have an easy to identify common denominator, because adding fractions, you do have to switch these to a common denominator. Okay, now we're not going to pretend these are here because it would just make the problem longer and more challenging. But does anyone recognize the common denominator of 2 and 4? Well, we could make this 4 in the numerator 2, because 2/4 is the same as 1/2. Now we add this, and you get 2/4 plus 1/4. And I can do that. You add the tops. 2 plus 1 is 3. But you don't add the denominators. It's called finding a common denominator because that's how you can add fractions more easily. Now, is that the answer? Let's look at this part. I wish it was easier, but this is what the challenge. When you just found the total, 3 over 4, that's actually the reciprocal of the answer, or basically the answer upside down. So what do you do whenever you find the total of your fractions? You always do the last step, which is to flip it over. And 3 over 4 flipped is 4 over 3. And that is your R total. Now remember, its unit is ohms. Okay, so you write each resistor as a fraction, 1 over, right? Let's clean this up. And let's do that again. I don't want to do the whole problem again, but 1 over 2, because that's the first resistor, plus 1 over 4. Common denominator is 4. And this becomes 2 over 4. 1/2 is the same as 2/4. Now add your fractions by adding your numerators. 2 plus 1 is 3. Check. 4 common denominator, check. Flip your answer, 4/3. 4/3 is really 1.3 if you want to turn it into a decimal. It's called an improper fraction. Okay, so here's the challenge, guys. We're going to take a look at the next page. It's on parallel circuits, one of our last lessons of the whole year. In fact, here are some of the answers, but we're going to go through the steps. I'm sorry I left this from a previous lesson. We'll just get this out of the way pretty quickly. Yikes, don't do that. You have to pick things. Sorry, wasting your time on the recording. Okay, so I bet once I erase all this stuff that you're going to realize that you've seen problems like this before. Okay, there we go. We're going to do the top problem as a sample problem. Almost there. And then you're going to do the bottom one That's your homework assignment. Okay, so I'm going to post this whole video and we're going to make sure we're totally understanding of kind of how to do this. Okay, let's make this efficient because you can always hit pause, you can always rewind. Okay, it says right off the bat, this is a parallel circuit. And I know that because even though it's drawn a little bit differently than the last one, I see a circuit where there's a node, which means the electricity can go either up to the 15, down to the 6, or it can go straight through. So that means the current is splitting, and that's the definition of a parallel circuit, 2 or more pathways. Okay, check, definitely have that. So it says the instructions are find the total resistance. Okay, so if step 1 is find the total resistance, I have to remember my formula. Not memorize it, but look it up. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, well, here are the resistors. How do I know the resistors? Well, they've got the classic symbol, the zigzag, and their unit are ohms, right? So that tells me it's a resistor. So let's not be afraid. Let's charge right in. So the first resistor is 15, so I write 1 over 15. The second is 10, so I write 1 over 10. The third one is 6, so I write 1 over 6. Okay, team, what do we do when we have a 15 and a 10 and a 6? We don't give up. We think about a common denominator. What number, what multiple, can we multiply each of these denominators by and get a common denominator? In fact, we're going to look for the lowest common denominator so we can add these fractions. And it occurred to one of my students that this would be 30. 15 goes into 30 twice. 10 goes into 30 3 times. 6 goes into 30 5 times. You may have to think about that or kind of play around and see, find the common denominator, but we won't make it overly challenging. So if we rewrite that, we get 2 plus 3 plus 5 all over 30. That's fraction addition. Quick review. Okay, 2 plus 3, that's 5, plus another 5, 10/30. Are we done though? Nope. We have to flip that. Flip it. So instead of 10 over 30, the answer is 30 over 10. Wait a minute, we can drop the 0. That's just 3 ohms. Okay? So we use math in our life once in a while, and this is certainly a challenging application of fraction addition. So 3 ohms of resistance. Next step, and we did this when we analyzed parallel circuits, is we're going to use Ohm's law. Ohm's law connects the current total of the circuit, the voltage of the battery, and the resistance total. So basically, it's for the whole circuit. What is the total current? And that's what step 2 is, current in the circuit. So here was step 1. We showed our work and we put it on the table. And now step 2, where you're going to use Ohm's law. So I is equal to, the V of the battery, it may be small print, but I see it right there as 10 volts over 3 ohms of resistance. Take out your calculator, use your phone. 10 over 3 is 3.3 repeating. But we don't write the bar over the 3, we just round off. 3.33, and its unit, because it's current, is the ampere, right? Voltage is measured in volts. Resistance is measured in ohms with the weird upside down horseshoe, and current is measured in amps or just A, right? Just a quick reference in case those get really confusing. So where do you put that? You put that in your table. Step 2. Okay, step 3. Step 3 is a kind of a cool one that we've already developed. Remember the idea that everyone gets the same voltage in a parallel circuit? Well, it's almost like it's too easy to be a step, But step 3 is everyone gets 10 volts, the same voltage as the battery, because every single electron can go back, gets pushed by the battery. Last step, step 4. Step 4 is to deal with the fact that you have 2 pieces of data about each resistor. You know its resistance and how much voltage it loses there. And all you're doing is you're actually going to use Ohm's law again, but now you're going to use it for each individual resistor. So I is equal to V over R. Okay, so in very small print, let's zoom in on this. V over R, 10 over 15. Because V, right, is the voltage, R is the resistance, 10 over 15. I can't do that in my head, but with a calculator, I discovered that that's 0.67 amps. 10 over 10, that's 1.0 amps. That's exactly 1. And then lastly, 10 over 6. That's 1.67 amps. And you're done. It's a marathon. It's definitely a test to see who can stick with multi-step thinking. But, right, when you do the bottom part, remember step 1, R total, 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Show your work, do it out, find the common denominator. Step 2, find the total current. Step 3, everyone gets the same voltage as the battery. There's your battery. So it's not really work you have to do. And then step 4, I would love for you to find the current for each of the resistors, right? Do it first for the first row of data, because you'll know the voltage by then. And then do it for the second resistor, and do it one last time for the third resistor. Good luck, and I'm happy to help.